I'm really very pleased to be here. It's a very impressive environment, both scientifically and also as far as arrangements. I'd like to thank the organizers very much. It was particularly exciting for me. Yesterday I liked very much accordion music, let's say Mirovic was a fantastic musician besides a fantastic mathematician, and all this group and organizers, in particular Nadia and her colleagues, Julia and so on. So it's very exciting. I'm going to talk about structured population models. So this is a topic that is a little bit different from most of the things you have been seeing so far, because it's mostly on the side of partial differential equations and models from partial differential equations in biology. But before I start, I'd like to emphasize 3 points, and I won't have time to go into them in this talk. One point is that I'll be talking about the so-called inverse problems, and at least twice today, perhaps even more, we have seen the word inverse problems appearing. In the last talk, Hermes Gadelia has mentioned one of the inverse problems that he solved. Then earlier, Andy also mentioned some inverse problem, and I'm sure many people have it in mind. So, in a certain sense, inverse problems are very much related to contour theory, and I'll just draw a small scheme here on the board. And the scheme is basically the following. Usually, when you do mathematical modeling, you have a model, and that means a set of equations and a set of parameters that make this equation to work, and somehow you feed in these parameters, perhaps some extra information too, usually initial conditions and whatever, and what you get is data, and this is what you observe. Now, in that sense, these parameters are going to control the results, and in the inverse problem field, what you want to do is to somehow recover the data. And needless to say, for this audience here, in a certain sense, you want to control with data. So you're trying to find the control parameters that give the data. However, there is one specific particularity of the approach that we take, is that usually these parameters are very tricky to find for several reasons. One of them is because you have a lot of noise in this data, and small perturbations in the parameters would give big changes in the results. So you need to know as much a priori information as you can about your parameters. In particular, you might need to use regularization techniques, and there's been a tremendous amount of work on these regularization techniques. In particular, here in the Soviet, in Russia, in the Russian republics, and there is a lot of work related to Tikhonov and his school. So this is a field that has been extremely explored here, and so I'm going to come back to that later in my talk. So that's the first connection with most of the audience here. The second connection, which I'm not going to have time to talk at all, is in the equations, in the PDEs that we are studying, we have to use some kind of techniques from partial differential equations, in particular entropy methods, or generalized entropy methods. And that's also, again, a relation to mechanics. So in that sense, I think I have justified a little bit my type from mechanics to biology. But let me go into my talk in a second. So the basic outline of my talk is the following. I'm going to talk about these structured population models, motivate, explicit the model under consideration, talk a little bit about the forward problem, which is this part that goes from the parameters to the data, and then jump into the inverse problem. So what are these structured population models? So those refer to population densities where you have not only the time parameter, but also a further parameter which is denoting some special feature of this population. For example, the size or the mass of the cell, the DNA content, the cell age by itself, the cell volume, and these are a few examples. The motivating biological experience that we had, or biological class of problems that we're working on, comes from E. coli, severe coli. Listeria coli, it's a horrible word to pronounce. It's common found in the lower intestine of warm-blooded organisms. They are typically rod-shaped, about 2 micrometers long and 0.5 micrometers of diameter. Average of these 0.6 to 0.7 micrometers cube. They have been extensively studied in in vitro and in vivo. And here are some pictures from, of course, white people. So, and this is one example where you find biologists caring about these problems. So these are observations of this N that I was talking about. And by N here, they call it frequency in the sense they take 1,000 or 500,000, whatever, of these observations, and they try to estimate the cell volume. They used to have some machines to count these. Now they have more fancy ways. This is from a paper back from '69 by this guy Kubitschek, by Physical Journal, and you see the kind of data that they have. And you see here there was linear growth and exponential growth. This refers to the specific models they are considering. But anyway, this is the fitting according to the model. So the actual raw data is what you see in the dots here. Okay. This is another example, and again, you see how noisy such data is. And so it shows how important a priori information and regularization is going to be. This is from a different type of model. It's cytometric data from tumor cell lines, and it's a much more recent paper. So now, what's the mathematical model?
Are we supposed?
Yes.
Are we supposed to understand the x and y axes of both of the previous plots?
Okay, you are. If I tell you one third information, which I thank you very much because, and please keep asking. I won't ask questions because I was trained in the Brazilian military tradition, which is you only answer when you really have a higher status asking you. But anyway, I'm going to actually answer the following question. So, I'd be glad to answer questions. Here is the basic point you caught already. Please stay awake because it will keep me honest. What you see here as far as this is the long time behavior. So it's an asymptotic state of the distribution of cells. So what they've done in this experiment, if you go back to my model here, is let time go to plus infinity. And look at what they see on the average as far as time goes by, because these things might change a little bit, but that's what they do. So the x-axis here is this cell volume, and this is the frequency. And time has been what's on this x, and this is what you said before. Is that clear?
This is a distribution of population sizes as time equals infinity from a large number.
Time going to infinity, yeah. Yes, that's good.
So it says that the cell volume, most of the cells have a frequency of 1.5.
1.5, yeah, 1.5.
The ones on the right are ones that went extinct, not so many, and the ones on the...
No, they happen to be not so often, just to know.
No, the ones on the left are extinct.
The ones on the left, yeah, probably there's a limitation for the measurement here, but most likely there is very, very few, okay? I mean, in fact, that's what you get from the analyzing the PDEs. So it disagrees very well with the models. And again, this is more interesting because in this model, actually, you see some oscillations here which are kind of interesting, but we haven't treated this data yet, okay? So you see a peak here, the second peak there.
And this is, again, probability on the y-axis?
Yeah, it's normalized.
And the amount of stuff on the x-axis.
Yeah. The end, you can choose whatever scale you want. I mean, it's number of, so you can put as probability, unit mass. So, by the way, this has a connection with some stochastic problems. Any further questions? Please keep me honest. Okay. So, now, the general kind of models we are considering from the mathematical framework. d dt of n plus ddx of g times n equals the integral from 0 to infinity of kx x prime and tx x prime. So this is basically a conservation law. It's very, very traditional conservation law. The time flow plus the change is equal to the total of cells that come from any other size back to the original size x, integrated from 0 to infinity. And if you didn't have this right-hand side, you would have, just a transport equation with some velocity g. And of course, in these models, from the forward perspective, would be pretty simple to solve. The issue here is how do you get to find your parameters, which are living in infinite dimensional space, k and g. And this is an extremely hard problem in general. I mean, anyone who has ever tried to solve this kind of inverse props can see how hard these things are. You have to make substantial simplifications and introduce further modeling assumptions. Okay? In fact, what we are going to be concerned with is a traditional doubling mechanism where you have a cell of size, let's say 2x, and it divides in a cell of size x. So here is the cell of size 2x, and it's giving rise to cells of, actually, you are losing a size x cell, and you are gaining cells that are coming from the size 2x. So that's what this equation is telling you. It's a particular case by choosing the right kernel here with deltas in the right place. I leave it as an exercise for you to figure out. This 4 here has to do with conservation of mass. I'll show it in the next slide why it's important. It's a pretty simple thing. Some people get confused with that 4, but don't worry about it. Don't even ask me because it's just a confusion. Okay, so growth of cells, ddx. dx, b2x describe the cell division. X derivative means transport to the right, where this functional term means transport to the left. So you see that there is transport to the right and transport to the left. There is a mix of these things. So it's not only transport that is playing a role here. There's a kind of backwards diffusion, which is important. Back to the tradition, let's say, if a biologist wants to talk to you, is probably not going to want to see the PDE at all. So you have to say something about the total number of cells. So that answers Annie's question again. You integrate from 0 to infinity, and you have your total size, your total cell number n, which may or may not decrease. You don't have conservation of cells in principle. You also have the important biomass quantity, which is integration from 0 to infinity of xn, which is a moment, it's a first moment of n. You do an exercise, trivial exercise, and you find out that ddt of n is equal to the integrated 0 to infinity of v of x n of dx. That means that whatever is birth over all sizes integrated against the from 0 to infinity is the total increase of the cells. So if B is 0, you don't have birth, then you have conservation of cells, but otherwise you don't have conservation of cells, cell number when it is cells. And then this is the intake, and this is the G. Now, from now on this talk, I'm going to make a very, very important assumption, which is important for our modeling, although there are lots of modeling and explanation, but there are lots of ways of generalizing what we did in this case. We haven't done it yet because we haven't had the time. So I'm going to take G equals 1 or G equals constant, which can be rescaled. This is important because there is another type of model where G is not constant anymore and it's linear with X. In that case, this is what they call exponential growth. Our models also fit that, our theory also fits, but we haven't worked out the details, so I don't want to even state that as a theorem. Okay, so what's the basic idea? And as a time-varying problem like that, it's still very hard, although you have a lot of data. Again, the amount of data you can measure is very limited. It's very bad data, and if you look at a transient regime, or if you don't have some kind of stable distribution, then you do have problems. Now, on the other hand, there is a very interesting theory coming from the IUTAM in Paris and Linia Eshik, who is in Stanford, but then originally from Russia. And they developed a very, very nice theory where they consider what happens as time goes to infinity. And they prove basically the following. If you multiply by a certain specific lambda 0, e to the minus lambda 0 t times n, then this distribution, which depends on time, converges in very good topologies to a constant times n, where this n is a function that solves this eigenvalue problem. So this is actually, I think, from the point of view of formal, it's not very hard to see how it works. Actually, you can do it formally very easily. To actually prove this right topology and right types of convergence, you need to use some very interesting techniques from generalized entropy methods, and so in a certain sense, it's like if you had some kind of Lyapunov function pushing into the right direction, which is this guy. Now, so back to Andy's question, so this is what you see, and you see that here you have to normalize this. So I was a bit concerned about telling you exactly what happened. I mean, that graph I showed you is after you do the right normalization. So somehow you have to take into account the time. You have to try to increase very much or decrease very much, but that's what you see for very general models. Any questions now so far, please? Okay, so these are examples, mathematicians' examples of such stable size distributions. Suppose, for example, you do the trivial case b equals 1. You see mathematically you expect this thing to go to 0. Well, actually, let me say a bit more. You are imposing that mathematically at 0, and the theory that tells you that it fits well at 0. I hope that's clear. And why do you say it's 0? Because, okay, cell size 0 is irrational. So you say, okay, no cell of size 0. Now, at infinity, you also have decay. You don't impose that as far as the initial value problem. You already assume that you have bounded solutions, and then you prove that, in fact, they decay infinity because of integration. Okay, here's another example. Just take some crazy function like minimum of 2 and 69 squared, so that's what you get. And you see, I mean, just at naked eye, you can't really tell much of a difference between this or that. I mean, there's a little bit more distribution on the right, but that's not great. Okay, so again, working towards the inverse problem, but still working on the specific well-posedness of the direct problem. Assumptions, let's assume that B is measurable and such that there are lower and upper bounds for your function B. That means that you cannot grow, you cannot reproduce too much, and you cannot reproduce too little. You can reproduce very, very small, but not zero. And then the direct problem here is from B you get lambda 0, which is the rate you are going to converge that stable distribution and this stable distribution. This is, I mean, the existence of solutions of this problem is a classical theory. I mean, it's related to the name of Brian and so on. So it's well known. What's important is that you have convergence rates to such solutions. So that's the kind of problem that we're going to look at. Suppose you observe n now, and how do you recover in a stable way this b from n and the lambda 0 rate? By the way, the lambda 0 rate you can also measure from physical experiments in a fairly stable way by looking at the total count of cells and doing the rate of decay of the total count. So lambda 0 is fairly stable, although subject to noise, evidently. What else can I say? Any questions? Geography is pretty big. Metz and Dickmann, Engel and collaborators from Austria, Pilat and Rondel, Gillenberg, and on the forward problem, Dumik and Gabriel, and there's a lot of other people. Okay. So there is an important adjoint problem to this forward problem. That adjoint problem, again, it's related to basic result of these matrices with positive coefficients and operators with some positive type. So this is a very general theory. Whenever you see this kind of problem, you have an adjoint equation. Although the theory is kind of tricky in this case, you have to do some further details. I'm not going to go into detail on that, but I hope you see here this analogy with the problems of Markov matrices, for example. Okay, so a little bit more of the direct problem, a few distributions to give you a sense of what's happening. So different distributions, different stable size distributions. I skipped that. So first thing when you do an inverse problem is analyze as much as possible what happens in this forward map. In particular, it's important to prove a few results, mathematical results about the parameter to solution map. So this sends parameter into data, this map here. So this map is from L infinity of R plus into Bm, capital M times L1, is continuous in the Wittstadt topology, is locally Lipschitz, is a class C1 in the spaces above. So the forward map is nice, smooth maps in these topologies. These topologies are natural, I'm not going to go into detail. We actually have worked with L2 spaces there. Okay? Now, how about the inverse problem? Okay, from the inverse problem, you would try to find, for example, B from the right-hand side of this equation. However, the right-hand side here you have derivatives, and these derivatives are extremely unstable. Well, yeah, you pose it, try to do it in practice, and you see it's a mess. So you have somehow to introduce regularization. It's well posed if you had these derivatives in LP, but then, okay, you would see too much, and you don't see that in practice. Now, what we did in our first works was a kind of trick for this particular model that works in a few other models, is kind of symmetrize the problem by adding a regularization term, and we put this red term here. This is a bit similar to trying to solve the classical integral equation, integral of lambda u equals v, which is equivalent to find the derivative of p divided by lambda, and regularizing by adding a derivative here. The idea of quasi-reversibility has been around for a while in this particular type of problems, for example, in the work of Latte and Lyons, but it has nothing for this particular problem. So this is the particular application we are using. And you have to prove something. We actually prove the well-posedness of the regularization. So that means we can actually show that if you add something to the right-hand side and do this regularization, you can bound your solutions in the appropriate way by finding this B alpha such that B alpha squared times ny squared plus this integral is less than the integral of f squared. Then you also show that the derivative is bound, of course, divided by alpha squared. When alpha goes to 0, this thing may blow up. And you get a derivative term also of that sort. Okay? So this is the kind of thing that we get. So those are the strong stability results. Now, how much the difference between the stabilized problem and the original problem account for? Well, assume that you have the solution of those two equations, be regularized and non-regularized, and you can prove an estimate of this form. Now you see the nice thing here is that you have an alpha squared, which is bounding your difference between the, let's say, raw solution, which is not feasible physically to invert, but exists in this model at least, and the computed solution. And this is the kind of thing that you get. Again, you have bounds by using the derivative of n, which says that you have to have information about n a priori, but that's something that you get from information a priori on beta, on b, I'm sorry. Anyway, this is what you get. And then, now suppose you add noise to your problem. So you put noise on the right-hand side, and by adding noise, assuming that your noise satisfies some physical conditions which are pretty reasonable, bounded from below and above, then you look at this more complicated equation. I'm not going to go into the details. And you get an estimate of the very classical Tikhonov type, where you have a balance between 1 over alpha here, the error that you get from the measurements, and the error that you get from the perturbation you are doing due to your regularization. And that's in the L2 norm. And now, of course, what you do is you minimize the right-hand side by choosing alpha as a function of epsilon. Very, very traditional way of attacking these problems. And what you end up is some kind of estimate on square root of epsilon. So we get some kind of weak stability of our regularized noisy problem. And again, this is blowing up with alpha. However, you have so you have to choose, again, coming back here, alpha as a function of epsilon, okay? And so back to my direct problem. So these are the solutions, and now we go and regularize. Now this is, let's say, pushing to the limit, worst case situation where you don't have noise, but you try to find things as approximately as you can. So this is b equals 1, and you see that close to 0 you have problems of finding this solution, but you still have something decent. So this is doing everything with all the information, and in the noiseless case. Now, in the noisy case, you get a little bit more interesting results. This is an analysis of the regularization that you get. So this is measures for the case epsilon equals 0, and using different methods. I'm not going to go into the different methods I'm talking about, but basically we have filtering, we have traditional regularization, and by Tikhonov. Okay, so again, this is the different results. Now, what's nice here is that you see as if you fix an epsilon and choose different alphas, you have bad results, then the results get very good, and then they become bad again. They have this L shape, okay? And this is actually the B times N, which is the reproductive factor B and the size N. In the noisy case, these are examples. You see here this shape of the curve. When alpha goes too small, then you don't have good results. There's an optimal choice of alpha. And you're going to ask, but how do I know this choice of alpha? Well, there is a technique that's very standard in the literature. It's called Morozov's discrepancy principle, and that's the one we use, of course. Okay, this is a reconstruction with standard white noise throughout the spectrum. This is numeric examples, and you see with the noise you get something. These are tests of the convergence rates, the square root of epsilon. You actually check that this is the interpolated line, so you see these results. Now, we also did a filtering reconstruction together with this regularization, so we filtered the noise a priori, and the results get a little bit better. I'm going to skip that for the sake of time. Okay, and these are real data results. I'm going to show a better slide later. So I'm just saying that this is joint work with Pedro Maia, who was a student from the University of Federal. Actually, Jair was one of the people who introduced him to us. Marie Domic from Paris. So we basically collected data from equalized birth rates, and this is the data that we had. These are the reconstruction. I'm going to show the actual data here. And so basically what we did here is, since we didn't have a lab, I'm still looking for a lab, and perhaps Hermes can provide a lab, perhaps with different type of cells, but I don't mind. Any cell is fine. Even half cells. Okay, so this is relative size data. What basically we did was we took the paper by Kubitschek, the one that I showed in the very beginning, and Pedro went there and very laboriously, in the old good grad student way, measured it with the PDF files, and with that he gave us his data. I'm going to finish okay? Okay, and these are the reconstructions. Now, there are a few details about this reconstruction. I wouldn't trust very much what happens in this, because if you go back to the data is extremely scarce here, and so subject to a lot of noise. So anyway, we get this as a result. This is a comparison if you do Tikhonov regularization the classical way. The problem here is that this is much slower because it involves solving a minimization problem with lots of parameters. We're talking about solving something with 1,000, 2,000, 3,000 parameters, a big minimization, nonlinear function, and so on and so forth. Anyway, this is a comparison between the two methods. You see there are discrepancies, and one has to work further to try to find what is the correct, if there is a way of finding this. These things are not that tricky to actually find, or you can do it numerically if you know the exact thing, but not really in this case. Conclusions. We are now working on some models of cancer and lymphoma growth, leukemia growth, so the model is much more complicated. So here is the model, and I'm not going to go into details. So this is part of our group. So this is Benoit Pertin from Jussieu, Anna Martiniak from Heidelberg, Marie Domic, Pedro Maia is now doing his PhD in Seattle, and Vinicius Albany is my student. Thanks for your attention. And I stop here. Thank you very much.
Question. Okay, then.
If there are no questions, wait, please. Let me do just propaganda.
Propaganda?
Oh, yes. Yes, but it's good propaganda, don't worry. I'd like to, since it's part of my being here is part of trying to establish international links between Brazil and other countries. I'd like to invite, especially our very, very nice guests who are hosts who are here, giving us a wonderful opportunity to participate in the series of events that we organize in Brazil. By we, I mean myself, Jack Euler, and a number of other people. So here is an example of the organizing committee. Sorry. So it's called Workshop on Mathematical Modeling of Biophysical Phenomena. You can find it at IMPA. So here is
Weren't we a little late?
No. This is a type of example that they did.
Yes, this is a previous. Wait, because but I can regularize backwards time by providing new events, and so you can find this at the site of IMPA. Anyone wants can ask me. So since my friend Hermes showed us some pictures of. I decided to show some pictures that they don't have up in the northeast of Brazil. So mountains and sea. And this is a picture of the last conference we had back in 2009. And I hope you can join us in this nice environment. Thank you very much for your attention and for your presence. Please ask me questions.